I've been tasked with somewhat of a countercultural program here, so I'll do my best. I'm going to, so my talk will be mostly about harmonic analysis and representation theory in the classical sense. So my topic is on Harish Chandra characters. And their relationship to the local Langlands correspondence. So let me begin at the very beginning. So if we have a connected reductive group over F, a local field, and for me, the real numbers are very much a local field, and I'll draw a lot of inspiration from that. And I'm going to actually start writing G for the F points of that group, so I'll use notation like this. And I have an irreducible complex representation of G. I'll maybe start dropping the word complex. All the representations for me will be complex coefficients. Then there is a function, the character, which is philosophically just a trace of the action of this automorphism pi g. That's only philosophic because pi is usually infinite dimensional, and this definition doesn't make sense. But one of Harish Chandra's fundamental insights was that one can make sense of it if one takes, instead of a group element, a compactly supported function on the group, and then one uses this to kind of smear the action of the group along this function. Then this operator all of a sudden does have a trace. In fact, this is over the p-adic numbers, this is the admissibility of the representation, which happens automatically when pi is irreducible. It's automatically admissible. And so this operator even has finite rank. Over the real numbers, it's a little bit more complicated than this, but nonetheless, we can define the Harish Chandra character as a distribution. And then it's a fundamental theorem of Harish Chandra that this distribution is representable by a function. So there exists a function, not necessarily on the entire group, but at least on the regular semi-simple elements of this group, which is locally, or I would say smooth, which in the p-adic case would mean locally constant, and locally integrable on the entire group. So however it extends to the singular set, it is not too terrible, so that we can integrate over the whole group, at least locally, which represents this distribution. So such that the distribution character is really given by integrating the function that we're trying to put into the distribution against this function. So in this roundabout way, Harish Chandra was able to make sense of this definition. See, if this would make sense, then just by linearity and continuity, you can, when you took the trace of this, you can just put the trace inside, and it will be trace of pi, and that will be this. And so Harish Chandra did the next best thing. And this function knows a lot about the representation. It knows about inequivalent isomorphism representations have linearly independent such functions, and the representation is uniquely determined by this function. And so studying this function, in particular studying its values, becomes a very interesting question because it can give us a lot of information about the representation. And for me, the guiding principle for my work and for this talk is the whole so-called Lefschetz principle, which was a philosophy expressed by Harish Chandra that real and p-adic reductive groups have to behave similarly with respect to their harmonic analysis and representation theory. So there is some kind of transfer of knowledge here between real and p-adic groups. In fact, there is a third part, which I'm going to leave out, but let me mention it, that automorphic forms over Q should also somehow behave analogously. So for me, that's not going to be relevant in this talk, but it is part of Harish Chandra's philosophy of Lefschetz principle. And initially, this is easy to see in kind of the basic results. For example, we know that parabolic induction is a powerful tool to construct representations, works equally well in the real and the p-adic setting. There are structural results like Curtin and Iwasawa decompositions and things like this work very well in both settings. There is a lot of parallelism. Where things become strange is when you start thinking about discrete series representations. So I'll discuss the classification in both situations, and then you're going to see that, at least from the outset, it looks very different. So here, Harish Chandra classified the real discrete series. The methods were basically partial differential equations on this real Lie group, whereas constructions of supercuspidal representations here talk about compact open subgroups. Those don't exist at all in the real setting, make no sense, and the concept of compact induction. And this uses very much the fact that this group is totally disconnected, that there are descending chains of compact open subgroups that go to the identity. That's a behavior entirely different from what happens on a real Lie group. So from that point of view, it seems kind of mysterious that you would expect that the outcome of such very different considerations should behave in a parallel and similar way, but that will be the topic of this talk. Over the real numbers, there is exactly even a subtlety as to what we mean by representations. There is the infinitesimal version of GK modules. Then there is various different globalizations. I prefer not to go into this discussion, but yes, there is something more to be said than over the p-adic numbers, where it's kind of a little bit simpler. But be that as it may, let me first talk about discrete series for real groups. I mean, the basic idea is if you try to understand p-adic groups, and if we believe in this principle, real groups are well understood. So let's see what has been understood about them. So here's the basic theorem due to Harish Chandra about real discrete series. First of all, G has discrete series of representations if and only if G has an elliptic maximal torus. Elliptic means compact modulo the center. Now the center may not be compact, and since it's contained in any torus, if the center is not compact, no maximal torus can be compact. But the next best thing is once you divide out the center, you may hope that there is such a torus. And there may or may not be. So let me make this remark right off the bat, that not every real reductive group has an elliptic maximal torus. SO2R does, but SO3R does not. And so that group will not have a discrete series of representations. Secondly, and if S exists, it is unique up to G conjugacy. So then, if it exists, let's fix it. Then there is a bijection between the irreducible discrete series representations and pairs of B and theta up to conjugation by the Weil group. Let me write omega R for the elements of the Weil group that come from real points in the normalizer. So the normalizer of the torus in this, which is the real points of my group, modulo the torus, where this is a complex Borel subgroup containing the torus, and theta is a character on the real torus with differential that is dominant for the Borel subgroup. The differential has to lie in the Weil chamber that is determined by this Borel subgroup. And finally, so this seems quite abstract at the moment. There's some kind of a bijection like this, but we can say exactly. So pi corresponding to b theta is uniquely determined by the values of its Harish-Chandra character. So here we come back to the main theme. And the values of its Harish-Chandra character on this particular compact or elliptic torus. And the formula is completely explicit. There is a minus sign in front to half the dimension of the symmetric space for G. And then there is a sum that looks exactly like the classical Weil character formula. On top, we have the character theta that gives rise to the representation, evaluated at the various Weil translates of the element. And in the bottom, we have a version of the Weil denominator. OK. So this is Harish-Chandra's theorem. It completely classifies the discrete series, and it does so in terms of their character. Now, I want to make a few remarks before I move on. One of the remarks that I already made is that such an S doesn't have to exist. If it does exist, it is unique up to conjugation. And because it is unique up to conjugation, we can reformulate this bijection here in the following way. Instead of having tuples of a Borel and a theta where S has been fixed, we can let S vary. And we can have triples, S, B, and theta, now up to G conjugation. That's another way to write the same thing. The reason I want to write it in this way, it seems a little silly, given that S is unique. But we'll soon be in a situation where S will not be unique. So we're already starting to do preliminary work towards uniformity. The next thing I want to say is that usually d theta is regular. So this d theta is going to lie in a certain integral cone. And this cone has walls. And there are few things on the walls. Everything else is inside. And once this is inside, it will determine the B. So we can drop the B from the datum. And so then we only have pairs, S and theta. One-to-one correspondence with what I could call regular discrete series representations. So this classification simplifies slightly if we decide to omit things that live on walls, because then we don't have to record the cone. Here? Yeah. So these are the real points. This is a normalizer in G of S mod S. And these are all real points for me. Real points of G, real points of S. Yeah, thanks. And if you have taught a class on compact Lie groups, like I recently did, then you've come across the following calculation of this character formula. So if you take, so that's part 3 of the remark, if you take half sum of the positive roots, then this thing can be rewritten. Oh, well, that's not a wavy. It's literally equal. This is literally equal to the following. Well, let's multiply both numerator and denominator by this rho. If you do this, then, of course, in the numerator, you're going to have theta times rho. And in the denominator, what you see is here you cancel half of this negative, and you add half here. And this looks nicer. This looks more symmetric. And in fact, it is more symmetric. Now you can see what the Weil group does. A Weil element just decides to make some positive root negative. But all this does is it flips the sign here. So this is a much nicer gadget here. It's Q invariant under the Weil group. And because of this, we can actually write this in a somewhat different form, where we take the denominator out. And in the numerator, we have the sign of the Weil element. And this is maybe another way in which you may have seen this formula written. So why did I do this? Because I want to draw attention to a certain formalism that this suggests. So at the moment, it seems quite innocuous. And when you, that's not the correct one. When you talk about compact Lie groups, then this torus is really compact. It is connected. The exponential map is surjective. And then you pull this back via the exponential map, where you have more room to maneuver because you don't have a torus. Now you have a real vector space. But if you don't do that, what you need to be mindful of is that both numerator and denominator are now not necessarily functions on S. Because we have this alpha to a half. I mean, we took a half of something, but we're not in an integral situation. And so this rho may or may not be a function on the torus. And Harish Chandra made a big deal out of it. He called groups for which rho is a function on the torus acceptable. And so he didn't want to accept the other ones. In particular, if you take the real points of a simply connected semi-simple group, that's acceptable. But PGL2R is not acceptable. Now, you can do something very simple. You can basically formally cook up a gadget where this rho becomes a character. So let's do this. What is it that we have? Well, we have the following sequence that comes from the squaring map. And here we have 2 rho, which certainly is a character of the torus. 2 rho is just the sum of all the positive roots. Each root is a character on the torus, so their sum, or in multiplicative notation, the product of these characters, is also a character on the torus. And what we want to have is a rho, which is a square root of this. Well, OK, we just make it so. All right, so we artificially construct this double cover of the torus. And then numerator and denominator are both functions on this double cover. And then one thing that you notice is that now the differential of theta rho is always regular. And so we can actually upgrade. We can kind of mash up those 2 points, 1 and 2 together, and have a clean parametrization of all discrete series at the same time. Namely, we're going to have pairs of S and a regular genuine character of this double cover. Genuine means that it doesn't inflate from S. It has non-trivial restriction to this plus minus. And all irreducible discrete series. OK. But at this point, it's a little bit unclear whether it was worth the trouble. Because yes, we got a somewhat cleaner parameterization here, but at the expense of introducing some kind of artificial-looking gadget that we didn't have to deal with before. So this will be kind of left as a cliffhanger for a moment, and then we'll have to reevaluate the usefulness of that in a moment. OK, this is as far as classifying representations is concerned. Now, let's look at the local Langlands correspondence in the real case, specifically for discrete series. And let me see. Does this say 41 or 47? 41. Did I speak for 20 minutes already? Yes. My goodness, this is awful. OK. This is not good. OK, so let's start with phi discrete. Now, the first construction was by Langlands himself. And Langlands basically did an ad hoc construction. He went into the structure of this, and he got out a character of a compact torus. And then he used the classification, and there was an L packet. Now, this ad hoc construction, if you want to think what is happening more generally, is very hard to see. But one can try to make it a little bit less ad hoc. One can try to fix an embedding of the L group of S into the L group of G, such that these factors. And then from the local Langlands correspondence for tori, this would give you a character of the torus, which it wouldn't be as ad hoc as just going and kind of by hand extracting information. The problem with this, however, is that this thing, there is no natural choice. So the ad hocness kind of gets moved into choosing such an L embedding. But at least you have a little bit more of a structure of what you're going for. And eventually, the cleanest formulation came from Adams and Vaughan. And Adams and Vaughan noticed the following thing. First of all, well, this is not really part of the theorem. This is a very simple observation, but I will put it here just so that all the statements are together. Discover S rho does not depend on rho. Rho was half sum of the positive roots, so we had to choose a set of positive roots. But actually, the cover doesn't depend on that choice. But here comes the actual, 2 and 3 are the actual observation. There is a natural construction of an L group for this cover, which is different from the L group of the torus itself. And there is a natural correspondence between parameters valued in this L group and genuine characters of the cover. So these covers behave a little bit like their linear cousins. There is a local Langlands correspondence for them. And here now comes the actual punchline. There is a natural embedding from the L group of the cover into the L group of G. Unlike the case with the torus, where there wasn't, for the cover, there is. And now using this, we obtain canonically a character theta phi on the double cover. And now we go back to, unfortunately, right here. So now we can use this upgraded, cleaner, natural parameterization of the discrete series. With this construction here, there are no ad hoc choices, and everything flows very cleanly. All right. So this is as far as I wanted to say about real groups. Now the question is, we want to go and look for the Lefschetz principle, so let's look at p-adic groups. Exactly. Those are the so-called genuine characters, which are exactly the ones that are not inflated from the torus itself. So they're -1 on the kernel. All right. So let's talk about regular supercuspidal representations. So here F will be non-Archimedean. And there is by now well-known famous construction of supercuspidal representations in this case. So these are irreducible supercuspidal representations. And the construction takes kind of a large amount of data. There is a whole collection of subgroups of the group. There is a collection of characters on them. And there is even a representation that you start with on the smallest one. So I don't want to explain all the data. That would take time, as is maybe not too important. I'll say just a little bit. So this thing is what is called a depth 0 supercuspidal representation of the smallest one. So there is a rational number, which kind of, just like the ramification of a Gallo representation, there is a rational number for a p-adic group, which kind of measures complexity. And depth 0 are the representations with smallest complexity. And they were already, at the time of Ju-Kang Yu, they were classified to a large extent by work of Moy and Prasad. And they're related to cuspidal representations of finite groups of Lie type. And those are understood to a large extent by work of Lustig. I just need to emphasize that one needs to discuss finite groups of Lie type that can be disconnected. And so the work of, a lot of the work of Lustig is for connected groups, although there certainly is also work on disconnected groups. And this comes about from Brouhat-Titz theory. Even if you start with a connected reductive group, Brouhat-Titz theory will produce for you disconnected groups over the finite field. So then the question is, how does this map behave? And Kim and Finsen have shown that this map is surjective if P does not divide the order of the Weyl group. So this is Finsen's stronger result. Kim had a weaker and less explicit condition on P. And fibers were also studied by Hakim and Mournihan, who showed that the fibers are quite non-trivial. It's not that one datum goes to one representation. Many data go to the same representation. And the data are related to each other refactorization by a process called refactorization. So there is an explicit procedure one can apply to such a datum to get another one. And then the equivalence relation generated by this procedure describes the fibers. So in sum total, we have a classification under some assumptions of all the supercuspidal representations. It's a classification that looks nothing like the classification that we saw for discrete series. So if we're interested in the Leschetz principle, we're going to ask the following question. Can we use pairs like this instead? And the answer is no. At least not in this generality. Why is that? Because we already know for finite groups of Lie type that not all irreducible representations, not all reducible cuspidal representations can be parameterized by pairs S and theta. And because that theory injects into the theory of p-adic groups via Moy and Persat already at depth 0, kind of the simplest case, if you cannot do it there over the finite field, it seems highly unlikely you would be able to do it over the p-adic field. However, you can, for almost all representations, it is OK still. So you cannot do it for all, but you can do it for a large class of them. If you're familiar with Deligne-Lustig theory, a pair of S and theta always gives you a Deligne-Lustig virtual character, which in general is not an actual representation. But as soon as theta is regular, which in this case means that its stabilizer under the Weyl group is trivial, then what you get from Deligne-Lustig theory is an actual representation. So we can call these the regular Deligne-Lustig representations. And then as theta becomes more and more singular, the Deligne-Lustig virtual character becomes more and more complicated. But what we can then do is, let's say, OK, we're going to make a definition. The representation pi coming out of Hughes' construction will be called regular if and only if its depth 0 piece is regular in the sense of Deligne-Lustig theory. And then it turns out that what we would like to have is, in fact, true. So here is a theorem that we have a bijection between pairs S theta up to G conjugation and regular supercuspidal representations. Now here this S is, as before, elliptic maximal torus. In addition, required to be tame, split over a tame extension. And this theta is a regular character. Regular means there's two conditions. One is that the Weyl group nothing in the Weyl group stabilizes. There is a second condition about the action of inertia on a certain subroot system of the root system that let me not specify that. But essentially, it is the same regularity condition as in the real case. A remark here, however, is in order. to compare a little bit with the real case, such an S always exists, and there are always multiple conjugacy classes of it. Unlike in the real case where such an S sometimes does exist, sometimes doesn't, and if it does exist, it's unique. Here it always exists and it's never unique. And this shows you, on the one hand, we have an almost exact parallel between how regular discrete series were parameterized by G conjugacy classes of such pairs. But on the other hand, behind this parallel real and p-adic story, there are differences, namely that here you have richer data. You have more data because basically owing to the richness of the arithmetic of the p-adic numbers. All right, so this is the classification. That already looks very nice and analogous to the real case. What about the character formula? So there is something tighter you can fix than the isomorphism class. You can fix the stable conjugacy class, and there still will be multiple rational classes inside. I think a nice picture to keep in mind is the picture of SL2, where you have a piece of the Bruhat-Titz tree, and then if you say, I want my compact torus to be unramified, there is exactly one isomorphism class of such, but in it there are two conjugacy classes, and they're distinguished by these two vertices. Each compact torus gives you a point in the building. When it's unramified, the point is a vertex, and the tori that sit over those two are not conjugate to each other. So that's already, but then you have ramified tori, and they sit over here, and in fact, there are two different isomorphism classes that sit over the same point. Yeah. So over SO2, you have three different isomorphism classes, and in each isomorphism class, you can have multiple conjugacy classes. Whereas over SO2R, you have one isomorphism class and, in fact, one conjugacy class. OK, so coming to the character formula. So this was studied over many years by various subsets of the following set of people. And so some of them studied the case of depth zero representations. Some of them studied just one step in the U construction. Then there was a question of, can you induct on U's construction? The answer is that's actually very hard because the depth changes, and you have to rebalance depth of various harmonic analytic objects in each step. So, but at the end of the day, we have a formula for the output of U's construction, at least in the setting of a regular representation. And the formula is the following. So this is a theorem where all of these people are involved. And then I did a minor contribution as well, because at the end of the day, what you get here are many, many complicated roots of unity that need to be somehow interpreted in a way that can be connected to the Galois side. And the formula that comes out is this, that if pi corresponds to S and theta, and if we pick an element in S which has p prime order, there is a formula without this assumption which is more complex, so let me not state it. But if we stick to this, then the character has the following shape. There are, first of all, some constants in front. The first constant is something very familiar from harmonic analysis. It's the Cotwit sign of the group. If the group is quasi-split, this is 1. So this measures how non-quasi-split the group is. And then there is a root number here, an Artin epsilon factor for a Galois representation made out of character modules of tori. And after these constants are done, you have a sum which is very similar as in the real case. Where you have the character that is used in the construction of the representation. And then there is a piece here, which is a piece of the endoscopic transfer factor. I don't really have time or energy to explain what this means, and it's maybe not too important, but what is important is the following remarks. So this is exactly the same as in the real case. These are the f points of the normalizer of the torus modulo the f points of the torus. The same notation as in the real case. The point here is this makes sense for f equal to r, and there it recovers the Harish-Chandra formula. So whatever this thing is, it ends up specializing together with these constants to the Weil denominator in the setting of the real numbers. And this is uniform for all f. And initially, I had required that p is not 2, but I just came back from Arizona Winter School, where progress was made even for p equal to 2. Although at the moment the progress is partial, let's see how far we go there. And then the third thing is that one can actually, and there is a lot that will hide behind this remark, one can enlarge the scope of both the classification result, which is there, and the character formula result beyond regular to what we may call semi-simple supercuspidals. Let me just say verbally what I mean by semi-simple supercuspidal. We started with use construction, which had a depth 0 part that by Moyen-Persat got reduced to a cuspidal representation of a finite group of Lie type. Our assumption was that this was a regular discrete series representation. More generally, such representations over finite group of Lie types have a Jordan-Lustig decomposition into a semi-simple and a unipotent part. The basic idea is that these representations are parameterized into what are called Lustig series, and each Lustig series corresponds to a semi-simple element in the Lustig dual group. So that's the semi-simple part. But then the members of the Lustig series are parameterized by what are called unipotent representations of the centralizer of the semi-simple part. And when I say a representation is semi-simple, I mean there is no unipotent piece. The Lustig series is purely semi-simple. So this took many years, and one of the things that came out of this was an observation of Lawrence Pice. That was that use construction is wrong. There is a flaw in use construction. So I misspelled the word wrong. What's the definition? I thought it would have been very on brand if I had the wrong spelling of the word wrong. OK, what's the definition of the word wrong? It's actually kind of funny. Because in the end, nobody really made an error, and yet an error was there. So you needed, so what is you doing? He's constructing representations by a compact inductions. He's compactly inducing a finite dimensional representation of a compact open subgroup that he's very carefully constructing. And in order to know that this is irreducible, this compact induction, you need to know that this finite dimensional representation, how it intertwines. You need to somehow know you have constructed it on the largest possible group. So there are certain intertwining properties which he had to prove. And to prove them, he was using the character of the Weil representation over finite groups of Lie type, which is something that enters the construction. So he's quoting a theorem from another paper on the Weil representation. He's quoting the theorem precisely as it is stated. Then you look at that theorem, and you look at the statement, and after a long meditation, you realize the statement is false. And then you go to the proof, and you realize the proof is completely correct. But what happens is that the statement doesn't match the proof. The final conclusion of the proof is different from the statement. So the person writing the proof didn't make a mistake. The person quoting the result didn't make a mistake. And yet there was a mistake. Nobody knows how this happened, but back. Except it's not clear they wrote the statement of the theorem, because that's a paper from the 70s. And those used to be typewritten. And it wasn't clear who the typewriter was. All right? OK, so and what happened was, as a result, the proofs of the intertwining statements were wrong. And in fact, Fontaine showed that not only the proofs were wrong, but the statements were wrong. The intertwining statement itself is incorrect, which means that the construction doesn't produce irreducible supercuspidal representations. What? The statement I just made? Oh, yes, thank you, sorry. No. Yes, thank you. The intertwining statement is wrong, which made the proof that the construction produces what it claims to produce wrong. But then Fontaine was able to find a different proof that the construction does indeed work. However, the intertwining statements that were wrong themselves are really needed in the derivation of this formula, in the general setting where you move through the different depths. And so this is joint work with Fontaine and Spice, where we correct use construction. There was a very subtle sign character that needed to be inserted at exactly the right place that ended up magically repairing the intertwining statements in their proofs. So then really you could use papers as before that had the effect of kind of negating the error in that lemma on the Weil representation. Using all of this, one can then enlarge the scope of these results beyond the semi-simple setting, beyond the regular setting to the semi-simple setting. OK, so this is about classification of supercuspidals, at least regular and more generally semi-simple, and the character formula. Now let's go back to the question of the Langlands correspondence. And what we initially had in the real case was a kind of a very streamlined construction of the Langlands correspondence for discrete series representations. But I want to do a little bit more. I want to not just have a streamlined construction here. I also want to have a characterization. I want to know that the thing that is being constructed there is a unique thing that one can possibly construct. So this is going to be a characterization and construction of LLC. Initially, this is the case, so I want to discuss discrete parameters with trivial monodromy, so no SL2 part. I'm using the complex version of the L group. So a full parameter will have an SL2 piece, and I want the SL2 piece to not contribute. OK. So what can we do, just purely abstractly? We can do the following thing. And I'm going to assume, as before, P does not divide the order of the Weil group, and G splits over a tame extension. Then I can do the following very, very simple construction. I can take the double centralizer of the image of inertia. I look at the image. Oh, sorry, wrong connected component here. I look at the image of inertia and I centralize it. And I realize the identity component is a torus, which may or may not be maximal. If the group is unramified, it is already maximal. But otherwise, it's still regular, so its centralizer is, in fact, a maximal torus in G hat. Now, I'm allowing here F. Am I? No. OK, I'm allowing F equal to R. But then this IF will be replaced by C hat inside of WR. The construction works just as well. And then this is maximal torus that's normalized by phi. So then I can take the product of this maximal torus and the image of phi, and I'll get a subgroup of the L group of G. And so what kind of a subgroup is this? What does it do? Well, first of all, it accepts the image of the parameter by its very construction. But secondly, it is trying to pretend to be the L group of something. It's an extension of the Galois group by this maximal torus. Now this maximal torus is abelian, which means this extension gives an action of the Galois group on this, which means that this is dual to some torus over F. And then this is really trying to be the L group of this torus, except it usually isn't. And let's recall over the real numbers, one can interpret the results of Adams and Vaughan as saying that there is a canonical isomorphism between the L group of the double cover and this script S. So at this point, we would be using the theory of the double cover in order to obtain a character. Now, the trouble is that, well, you can make this double cover. You can define it in this setting with the same definition, but this doesn't work over QP. In fact, theses were written on this subject. This was tried for many years, but it didn't work. But something else does work. A Galois construction works. So I want to give you the example of the group PGL2 over F. F, any local field, Archimedean or non-Archimedean. In that example, the torus is going to be E cross mod F cross for any quadratic extension E over F. And there is an obvious cover of this where you don't divide by F cross by the subgroup of index 2, which is the norms from E cross. So this is a double cover, but it's defined Galois theoretically. Now, let's think of what happens when E over F is C over R. Well, then what you have is R cross over R positive, and then C cross over R positive, and then C cross over R cross. But in here you have the circle. This is equal to, when you embed the circle into C cross, this is just the circle. And you can embed the circle into C cross here. And here you have the squaring map. And so you see that this Galois theoretic construction becomes identified with an algebraic construction of taking a square root out of here. But over a non-Archimedean local field, even though you can write this, this will not be surjective. The circle, the p-adic circle, the squaring map is not surjective. So that's why this doesn't work there. And since the difference between the cover and not the cover is a plus minus, you'd be gaining a plus minus at one spot and losing it at another spot. And then you're in a similar misery as you were before. And now, the point is that this silly construction for PGL2 actually can be generalized to an arbitrary group and an arbitrary torus. And then one obtains something very nice, which you can probably guess what it is. Namely, the following basic thing. Number one, well, that's not really a theorem. There exists a double cover of S, naturally associated. So that's not part of the theorem. That's a construction. But the theorem starts here. Also no. There is a construction of an L group. OK, so maybe this is -1, and this is 0. And now comes 1. There is a one-to-one correspondence between parameters for this L group and genuine characters of this double cover. And 2 is there is a natural embedding of the L group of the double cover into the L group of G. So this generalizes to any local field the results of Adams and Vaughan over the real numbers of the existence of the cover, the existence of its L group, the local correspondence for genuine characters, and then the canonical embedding of the. Well, but now we're in a good shape because we understand characters. We have generalized this, so we can actually now give a characterization of the correspondence as follows. We obtain completely canonically a genuine character of the double cover of these stores by the same procedure as we did before. So the parameter is valued in this group script S. This group script S, this embedding here, factors as an isomorphism to script S, which means that from our discrete parameter, we get a parameter for this double cover. We get the genuine character of the double cover. And then we can write a candidate for the stable character formula, which looks exactly like the previous thing. Only one minor difference. Instead of taking the rational vowel group, I'm taking the rational points in the absolute vowel group. But then I'm going to write exactly where this a plus minus is a genuine sign function, which is explicit. And then the conjecture is that the packet associated to this parameter consists exactly of those representations that decompose this virtual character. This consists exactly of those pi whose elliptic scalar product with this stable character is not 0. OK, so that's a characterization of the correspondence for supracuspidal parameters. And for a while, it seemed to me that this is as good as one can do, because we don't understand discrete series representations as well. We don't understand their characters as well. But recently, there was a wonderful idea by Chi-Hang Lo and Cheng-Chiang Tsai of how to bootstrap from this and give a unique characterization of the entire correspondence for any arbitrary parameter whatsoever, using this as a base. So this is ongoing work. I don't want to say details about it. I just wanted to advertise it here, that even though initially this seems like kind of constrained by the scope it can handle, it actually can handle the entire scope. And moreover, this conjecture now can be turned into a construction if you combine the conjecture together with our knowledge of the classification of semi-simple supracuspidals and their character formula. You can say, well, I know what I'm shooting for. I know the characters of all semi-simple supracuspidals. I can just go back and import that information into the construction. And then this leads to an explicit construction of this set. Yeah, maybe I'll stop. The yellow is really blinking here. OK, so thank you.